Welcome to another exciting computer architecture class. Hope everybody had a good break. And what I do is wrap up a topic that I'd been putting off for a little while. Then this is the topic of microcode. When you try to create a new CPU, oftentimes you get involved with creating new instructions, and each one of the instructions has to be able to go through a generalized process, which we've discussed before. And this is a process that involves decoding an instruction after a fetch, executing the instruction, storing the results, and then going to get the next instruction. And one of the things you might like to do is you might be tempted to hard code the finite state machine for executing this process. And in fact, this is exactly what we learned how to do in Digital Design 1. But as you all know, that what we did in Digital Design 1 was not necessarily the thing that they do in industry. In fact, the way to do this is to execute a program that's stored in the hardware, and it is called the microcode of the machine. And you can actually code a CPU in microcode, and it gives you a very symmetric sort of instruction set. And so what you can do when you go to create new instruction set architectures is you can create new microcode programs that will give you new architectures. There were several machines that used microcode. The Amdahl machines, which later became known as Amdahl, AMD, you may remember. The A for AMD is Amdahl, in case you were wondering. The Amdahl processors were copies or clones of the IBM mainframes. So Amdahl was making clones from the beginning. And as it happens, Lamb, I think you've got your microphone open. As it happens, AMD is making clones even today. They make the clones of the Intel processors. And sometimes I think they do a little bit of a better job making their clones than Intel makes, does as originators of the CPUs. So when we think about where we might find the microcode, we see it now in microprocessors such as the 68000, the 68020, 68030, 68040. We see it in the RISC processors such as PowerPC, the ARM, and also the new RISC-V, which is intended as an open source RISC processor, an alternative to the ARM that you don't have to actually license. And so microcode has permeated most of the CPUs that we encounter today. The CISC, of course, we would like to see it microcoded because the instruction set is so complicated. The RISC, on the other hand, can be hardwired, and therefore, because of its pipeline and its hardwired nature, can execute one instruction per clock cycle or faster, depending upon how deep the pipeline is. There are these things called very large instruction words, and we can basically create our microcode in what is essentially an FPGA. So if we become FPGA programmers, that is, we write VHDL or Verilog, then we're able to create very wide instruction sets that are able to do multiple things in a single CPU cycle. For example, you could do an add and a multiply in a single instruction, and that may be a very useful sort of thing, and you could hardwire it. And then, of course, there's the Java virtual machine, which is a software interpretation of a set of instructions. And so that's almost like having the microcode in simulation. So then comes Intel, and he decides, oh, maybe what we'll do is we'll get rid of the CISC microcode, and we'll use the hardwired pipeline approach. And because this is a little bit more efficient, we'll essentially implement our CISC instructions in hardware. And there's some other variations, such as hardware Java virtual machine implementation in the ARM Giselle, which I don't think is very mainstream at this point. So what happens with microcode is you're kind of trading off a little bit of space for flexibility, right? So this enables you to change your instruction set architecture. So if you decide your CISC machine is better off with a different set of instructions than another one, you can design that instruction set specifically for that CISC machine hardware, and you do it by programming the microcode instructions. This is what an IBM 360 looks like. I would say that when I first got started with the IBM mainframes, it was an IBM 370-165, which was really very close to this one, all programmed with punch cards and COBOL and Fortran, things like that. These tapes over here, which you can see, these are 2,400-foot reels, and I think they were running at about 1,400 bits per inch. So these things did not hold very much data. And that's your punch card reader right over in there. This here is your front panel. And I don't know what this dial over here, this analog voltage readout is. It may just be that, voltage readout for the power supplies. They made a very compact little front panel, but if you were to look at the side over in here, it goes pretty far back. So this control panel is very similar to the blinky lights you might have seen in some of the more modern computers, such as the PDP-8 and the PDP-11. So this is an interesting point, because what happens here is you really want to have a mechanism for control of a large machine that's compact and easy to work with. This person here is probably using the equivalent of an IBM Selectric typewriter. It'll have a type ball in here, which prevents the keys from getting jammed. And I think what happens is IBM starts to create industrial designs that look really nice to me. I mean, you could turn around and just start to do work in this little desk area, and that's part of the computer. In fact, this little console in here is part of the computer. So IBM designs, we're getting pretty far along. We've lost that sense of design, I think, in most computers. So what we'd like to do is think about our architecture in terms of arithmetic operations, data path, and a control sequence. And the control sequence is going to essentially move data from one place to another, into and out of the ALU, the arithmetic logic unit, into and out of registers, into and out of an instruction register, which is used for decoding. And then we'll have a thing called the program counter, which is kind of like your finger keeping track of where you are in memory. And every time you go to get another address, you'll be incrementing the program counter. And if somebody executes a jump instruction, you'll be jam loading the program counter, so you'll jump to that new address. All of this starts out as getting mainstream once, and this is still during the era of tubes. Maurice Wilkes over in the UK starts to create the so-called EDSAC computer. So we don't actually have microcode for ENIAC, but we have microcode for EDSAC. And so what you can do is you can actually see a picture of the EDSAC, and that's what it looked like. And these are what they call relay racks. Relay racks are borrowed from the phone company. They're meant to hold relays, but in fact what they're holding here is tubes. And the relay racks are all 19-inch. In fact, they standardized on a 19-inch rack because they were created in 1919. It was a standard. And you can still get relay racks today. In fact, you can get full-sized racks with depth and with doors, and you'll see them in regional data centers, all standardized on that 19-inch dimension going across. The interesting thing about the microcode is it leads to a very symmetric looking piece of silicon. And when you look at the micrograph of the chip that has the microcode in it, you'll see very regular read-only memory used for holding the instructions. And so that'll go into some decoder, and then that controls how the finite state machine works. So the finite state machine, that is the instruction fetch, instruction decode, instruction execute, and then instruction store, that is a four-step finite state machine, which can have many different instructions, and all of that gets microcode programmed into the read-only memory. And if you remember your finite state machine design, you'll remember that there is combinational logic. Well, this is part of the combinational logic. That's a lookup table. And so that'll get you to do the next instruction and describe how that gets executed. So people who write the microcode ROM, these are the microcode programmers. They're the designers of the instruction set architecture. And what they'll do is they'll create new operational codes, or opcodes. And these will be machine code instructions. So for example, you could have a special instruction that says no operation, which does nothing for one cycle. And that could be inserted for the purpose of delay. So,
Professor?
Yes.
Is it then limited to only the instructions that have been on that matrix? Like the computer then can't do anything not already as one of those kind of like operation points on the microcode ROM?
That's exactly right. You design, when you're designing your CPU, you want to design the number of operational codes that will be included. And your design will be characterized not just by what you include, but what you decide not to include. In fact, this is the same for designing of languages. Sometimes we define a language as much by what we leave out as what we put in. So when we think about our decisions about which instructions are important, hopefully we've decided to profile a number of compilers and looked at the instructions that were created, and we were able to make a decision that 128-bit floating point multiplies are used so infrequently that we won't have a direct implementation of those, but maybe we need 32-bit multiplies and we don't need 64, and we certainly don't need 128. And if you're thinking, well, all right, let's do the whole thing with, a 32-bit machine, you've made a decision. You can't multiply in hardware the 64-bit numbers. So what you end up doing is you make a trade of space for time. Now, if you want a double precision multiplication, you've got to implement at least part of it in software, assuming that you only have a 32-bit floating point multiplication available in your hardware.
So if you were going to create like an operating system to go in tandem with this, you couldn't do that like in another vacuum. You'd have to know like abstractly how the microcoded, like how this whole microcoded CPU, like the kind of contract that is set with it, or could you just do it and then it would kind of work out?
Yeah, so that's a great question. What happens when you design your instruction set is you go through a process whereby you make a decision about which operational codes you would like to include. When you design an operating system, oftentimes you create a set of features that have nothing to do with the instructions. So for example, I'd say to you, I want to run Intel CPUs. I like Intel inside. I'm comfortable with it and everything. Well, I can find the binary operating system for Fedora and Linux and Ubuntu, and I can get those already precompiled for my 32-bit machine. But then, somebody says, I think maybe I'd like to use a Raspberry Pi. Well, the instruction set is totally different. I say, yeah, but it can still run Linux. It still runs Ubuntu. It still runs, Fedora. So as a result, I can proceed to get those things to either be already compiled for that instruction set architecture, or I cross-compile it for that instruction set architecture. So the whole operating system might have to be recompiled in order to make a version that's compatible and perhaps optimized for Raspberry Pi 4, because Raspberry Pi 3 was a 32-bit machine and Raspberry Pi 4 is a 64-bit machine. And while the 32-bit machine code would run in the 64-bit machine code, why would you want to? Just recompile it. bite the bullet, recompile it, and distribute the 64-bit version and tell everybody, look, if you're on a Raspberry Pi 4 with 64-bit instructions, you really want the 64-bit version of this operating system. So it might, have extra instructions for doing 64-bit multiplies and divides and yada, 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 all these other things. But as a result, if you really want to take advantage of the hardware and the microcode, you got to recompile. So first thing you're going to need is a compiler that's going to be capable of optimizing for these opcodes. And so therein lies the rub. If you really want to design something for the specific microcode that you've got, then what you need is a compiler. Now, if I told you, well, I really want Java because I really like Java and I'm Doc Java, then that's kind of true, actually. So then maybe I'll do a microcode like Giselle, which is kind of like for an ARM processor, only I'll make it so it runs the Java virtual machine opcodes directly. And so then you've got a 32-bit machine running on an ARM processor, which is, it's meant for that. That's okay. But it now executes Java virtual machines very quick. But then you say, oh, but I need an operating system. Well, therein lies the rub. We don't have one already compiled for the Java virtual machines instructions. So we'll have to recompile the whole operating system for that. But maybe that's okay. And once you've got a good compiler and you've got a good operating system, everything else can get recompiled as well, which, well, that might be a pain, but there it is. That's the price you pay for changing your instruction set architecture. So that's my long-winded explanation. So yeah, as it happens, what happened, we go through a process which allows us to transition from relays to vacuum tubes. They create the electronic numerically controlled computers like ENIAC. And then we switch from vacuum tubes to transistors. In the process, we need a place to store data. A lot of times what people were doing was they would create mercury delay lines, and they would use acoustics to emit the data from one end of a delay line and then read it back from the other end. And the delay line would store the bits in the form of percussion waves inside of the mercury acoustic transducer-based columns. I actually have a calculator in my office that uses an acoustic delay line for storage, and it does a multiply that's extraordinarily slow, and it's completely electronic. So it's a really fascinating sort of piece. It's a Monroe calculator. And then people decided they could store things using either vacuum tubes or magnetic cores or transistors. And the magnetic cores require that you magnetize a piece of iron and then read the collapsing magnetic field when you go to read the magnetic core. And people would thread these up by hand, believe it or not. Very fine work done under a microscope, and you could make magnetic core memory. I made one of these diode matrix read-only memories in woodshop back in junior high school, and that's a form of read-only memory. Basically, you can use anything that allows switches to make and break contacts. So I started with a juice can, wrapped it with graph paper where the squares were cut out, and then had paper clips making contact. And you could turn the juice can and it would read out the data. You could use punch cards, you could use paper tape, whatever you like. Logic, is expensive compared to the storage facility. So read-only memory based on diodes is pretty inexpensive. Read-only memory based on magnetic cores, that would be terribly expensive. So at that point now, the difference is the difference between being able to read or being able to write it. And as a result, ROM is way cheaper than RAM because diodes are generally cheaper than trying to create a flip-flop out of vacuum tubes, which is hard. I mean, you need at least two vacuum tubes for that. And in general, we could find that ROM was faster than RAM. And so cheaper, faster, smaller, that sort of thing. So when you do your microcode, you put it into ROM. And so that would mean that the instruction set can't be overwritten. Now, it is the case that you could, in theory, create a RAM-based instruction set, but then you'd have to reload the instruction set every time you booted the machine from a power off situation, which would not be good. So then, these people come up with these ideas of doing instructions that are going to facilitate multiprocessing and concurrency and parallelism. And so as a result, they come up with new ways in which to do multi-core microcode programming. And then over at Berkeley, they come up with this thing called the RISC-V CPU. And you may not have heard of it, but it's starting to get a little bit of traction. And what it does is it enables you to essentially do what the ARM does, only it's open source. And what that means to me, the instruction set architect, is I can just download this thing and come up with my own instruction set architecture. And if the RISC-V specification is implemented in something like VHDL, well, hey, I can just take that VHDL and drop it into my DE2 card with my Altera Quartus program, compile it, and now I've got an FPGA that thinks it's a RISC-V processor. Now, if we wanted to do that today, Altera supports a RISC instruction set-based processor called NEOS, which allows us to do hardware-software co-design. But we don't normally reprogram NEOS's instruction set. In fact, if we wanted something like RISC-V, not only would we find the full-blown VHDL available, which is cool, but we'd even find compilers that support it, which is really important if you want to start writing programs in C and having them actually compile to this RISC-V processor. Because once you got that, now you can bootstrap the cross compilation of a whole operating system that's going to run on your little FPGA. Now that's a funny thing to do. I mean, I did this once. I actually got Unix to run on an Altera Cyclone using the DE2 boards. And it's a micro Unix, and it ran X Windows. And I thought, man, that is slick when you can get stuff like that to work. So once you're doing that, you're basically taking the FPGA and using it as a CPU. And one could make a compelling argument, but gee, why don't you just buy a CPU and use it as a CPU? And I'd be like, yeah, you can do that, but then you don't get the ability to write your own instruction set architecture, which is really the kind of thing you might be interested in doing. To date, nobody at Fairfield University has been writing their own instruction set architectures, and with good reason. There's plenty of good ones out there. You need a good reason to write your own. So, having said that, that doesn't mean you shouldn't or that you couldn't. In fact, maybe you should, and you certainly could. So when we start to think about these instructions, we think about whether we're going to support 16 bits out through 64 bits. And hey, why shouldn't I make 128-bit architectures? I mean, that's a legitimate thing, right? I can do that. Why not? Of course, you might say, well, why would you want to, right? Because the amount of effort it takes to support 128-bit wide words could be very high, and the benefit might be very low. So there may be diminishing returns in going beyond 64 bits. In fact, even 64 bits had diminishing returns sufficiently enough so that when the new ARM processors came out, they were all 32 bits until we got to ARM 4, the Raspberry Pi 4. And so that was a key that I think sort of changed the way in which the microcontroller-based folks started to look at the Raspberry Pi. I mean, it was a lot of angst going on when they said, oh, we're going to have a computer that costs more than $35. And now Raspberry Pi 4 has essentially broken the mold on the $35 limitation. Once you create something with enough features and with enough cost of goods, you can't keep charging $35. eventually you've got to raise the amount that you spend. So when you're looking at these microcode functions, there's usually a bunch of different arguments. Here's the operational code, but then there's a destination register, a source register, and maybe another source register. So maybe you want to add this to that and give you a function that says add these two things, make that. You know, there's sort of a problem because you want to be able to gain access to these things. And if you don't want to have to go out to some register in order to find the two things that you're trying to get, it might make sense to have it, you know, all local to within the CPU. You don't want to have to go out like to memory and find and try and retrieve arguments to A plus B equals C. You know, that doesn't make sense. Your computer will get bogged down with I/O. So now our finite state machine has a whole bunch of things that it has to control. It's got to control the program counter, the registers on the CPU, the ALU, memory address register, and it has to have an instruction register. And it's all these things it has to load and control and decode. And the ALU, you know, it's going to have an operation that's part of the function that's going to feed the ALU. And ALU chips, you know, from the days of yore, back when they had 7400 chips, ALU chips all had opcode instructions. So give you an example. It's not too far-fetched. The 74181, if memory serves, is an ALU TTL chip. 74181. So there it is. This is a what you call an arithmetic logic unit with 4 bits. Oh, do I want to pay Amazon? No. Close this nonsense. So when you look at this ALU, this arithmetic logic unit, you can use it to build a computer. And in fact, people have done. And what it does is it gives you a series of arithmetic logic opcodes. And here are the opcodes over here in binary. It's a 4-bit machine. And you can see it does exclusive OR, it does add, it does logical AND, it does logical OR, it does NOR. It's got all these different interesting functions, which we all know and love. And in fact, it does them all in hardware. And so you can get one of these guys and hook it up to another one, and you'll have an 8-bit arithmetic logic unit. They call this MSI TTL because they say it's medium scale. Well, it had 75 logic gates. Now, if you consider that medium scale here in the new age, well, there must be something wrong with you. But back in the day, when this was created, that was considered a lot of gates. 75 gates was a lot of gates, believe it or not. And then it says here we had a Schottky version, the 74S181, that could work in 11 nanoseconds, 90 megahertz. And then we got another one that worked in 7 nanoseconds, only 143 megahertz. So these things did not run that fast, especially when you consider modern CPUs are running at gigahertz. So in their day, they were fast. But it's interesting to note that you could build your own computer using this discrete logic and then proceed to do your own microcode. And in fact, if you look at the original PDP-8s, you couldn't open up the box and find the CPU because it was a bunch of these chips, these 7400 chips that were used to create the CPU. And so you couldn't find the microprocessor because it was distributed across many TTL chips. So that's an interesting point. You know, all this stuff got started from the old days of TTL. So the RISC-V has a very familiar sounding sequence of events that it has to go through. Got to fetch the instruction, decode the instruction, do some kind of operation, store the instruction somewhere, figure out what the next program counter address will be, and then repeat. The microcode sketches for an instruction fetch might look like this. These would be the mnemonics. And then eventually what will happen is you'd want to implement this perhaps in VHDL or Verilog, whichever you prefer. And then that would give you what I would call a low-level finite state machine design of your central processing unit. Here's one for loading a word. Here's a branch. Here's jump to an address. All these different things have to be coded, microcoded. This jump to an address, we might take a prior address and increment it, and then do a jump immediate, which loads a program counter with the current address plus the offset. PC is the program counter. And then the next time the finite state machine starts a new cycle, it'll use this program counter to proceed to repeat and load another instruction word. So that microcode programming is not something that most people will ever do in their lifetime. I have never done any microcode programming. That just sounds like you need a good reason to want to do it. I've always taken the instruction sets that were created for me and just made use of them. But having said that, if I had a good reason to want to microcode my own computer, I think, there's compelling argument we could do that. And we could probably start with the framework based in VHDL, download the new microcode into the FPGA, and then test it. Presumably, it would make sense to do it if you wanted to implement a machine in hardware that you didn't have a hardware implementation for, like a Java virtual machine. Is then you could make use of the compilers that already exist. If you go down the path of creating your own opcodes, your own instruction set architecture, and it's really new, you don't have a compiler yet. So now you have to go back, now that you've made your CPU, now you got to go design a compiler that's going to generate the opcodes for that CPU. That sounds like a lot of work to me. And after that, you're going to want to recompile your operating system. Not easy. A lot of work. You need a good reason to do it. So here is the sort of hardware code for doing the operations in microcode. So here we see a program counter being set equal to some address plus 4. Here's another example of, we'll call it microcode language. It's got its own little sort of register to register control language, which looks familiar, right? Because you've probably seen this if you've done any VHDL programming. So this is a sort of a little overview of the microcode. I didn't want to get too deep into it, but I did want to let you know that you can find microcode CPUs. They're open source, such as the RISC-V. They're starting to get a little bit of traction. Nothing as popular as the ARM processor from Broadcom and ARM, as is embodied by the Raspberry Pi. Have people here tried using the Raspberry Pi? Have you seen one before? Never seen one? If you've never seen one, you got to see one. Let me bring one up here.
It's on the Christmas list.
It's on the Christmas list. Good. Yeah, I've got a bunch of them actually. So here's a Raspberry Pi. I was going to set one up to do network storage. There is no Raspberry Pi 5 yet. I think we can see some pictures. Let's look at the pictures. Yeah, there we go. So what they did, you can kind of see it in here. These blue USB interfaces are Raspberry Pi 3.0s. And this little boxy RJ45 jack is your Ethernet going at 1 gigahertz. It used to be Raspberry Pi wouldn't support gigahertz Ethernet, and it wouldn't support USB 3.0, but now it does. But it came at a price. Instead of a $35 machine, it's now a $55 machine. And that's, still quite reasonable. This is a quad core, I think. Let me just check. They don't tell you. Oh, and you can get it with more RAM, but you can't upgrade it. So when you get it with the extra RAM, it comes soldered directly onto the board. Just you can't add any more than that. And I've always felt like the 8 gigs of RAM would be worth it, but then they charge extra for that. Here it's $75 right now. That's quite a bit higher than the $35. In fact, for $35, you can get a Raspberry Pi 4, but now you've only got 2 gigs of RAM. I'm not sure what I'm supposed to do with a computer with 2 gigs of RAM. It doesn't sound like enough RAM to me, especially if you're going to use like this little CS bus connector and put a camera on it or something. You're just going to crash the computer and run out of RAM. So that's not good. These little GPIO pins coming out the top, that's kind of like the Raspberry Pi, the Arduino bus. They've got their own little bus. And the shields that go on top, those are called Pi hats. So you keep stacking the Pi hats on. And so a lot of times people will build a Pi hat specifically to something like Raspberry Pi 4, and then they'll say, here's a Pi 4 hat. And then they can charge you extra for that because it's got some sort of demand associated with it. This has got a USB-C connectors. One's for power, the other's for data. It's got a mini HDMI connector. It's got a audio out, and there's the USB 3. You can tell because it's blue. USB 2 is over here on the left, and that's the 1 gigabit interface. And this takes a little SD card down at the bottom. That's where your operating system would go. And there's the SD card. And that's about it. That's the system.
Professor, to operate these, other than the power supply and the SD card, do you need anything else?
Be nice to have a keyboard and a monitor.
Okay.
Yeah, you want to get something to plug into the HDMI input. And here it is, HDMI input. And then you also want to do probably a keyboard onto or a mouse, right? What was I thinking? You'll want a keyboard and a mouse. You'll want the Ethernet. Probably want to get the extra RAM, and then you're going to need an SD card. They don't come with it. A little 16 gigabit SD card. You want to get a class 10, something fast. Don't slow down your computer by cheaping out on the card. In fact, 16 gigs might be a little bit on the shy side. You might want to opt for something a bit faster. Once they put gigabit Ethernet on here, and they put the USB 3.0, they basically gave you all the hardware you needed to make a functional storage area network disk controller. So you can basically add USB 3 hard drives and put them on the network. It's sort of like building your own little time capsule. I don't know if you guys are familiar with time capsules, but it's just an embedded controller for storing data on the disk, so you don't actually have to plug it into your computer directly, which would probably be faster, but it might be okay to have it on the network like this, running at a gigabit per second. Still slower than USB 3. But you really don't want it to act as a hard drive server going through USB 2, because that's just way, way slow. And then if you have a camera, you can either plug that into the USB interface, which will be slow, or you can get a Pi Cam. I have one of those, and you can plug it right in here into the CS1 interface. That little black area right in here pops up, and you throw the ribbon cable in, and then you push it down, That's how you install the camera. It gives it a very high bandwidth interface to the computer. If you're going for like a kit, I think they charge you the big bucks. These guys where they're selling you everything, including the case. I don't
It's like
know. Like,
$100 starting.
yeah, $100. I think so. Yeah, you probably want it with the heat sinks, and you know, you don't theoretically need a heat sink, but then you don't want to have it throttle down when it gets hot. And you can see the Pi 3s are still $34 at Best Buy. I didn't know Best Buy had them. Here's a kit, the Pi 400 kit. Now this one, I think it comes with the keyboard, so the whole Pi is integrated right into this keyboard in here. Now I did the teardown video on that. I saw what it looked like, and they really did a lot of work on this, and that kind of makes it nice. Computer for $100, Pi kit. So they bundled it nicely. Me personally, I set these things up with a mouse and a keyboard. Then I operate the whole thing headless, and I just go in remotely using SSH and VNC. Here's a this is quite typical. The Pi Moroni is a fanless heatsink. It's just a mass of metal, and they stick that on top of the hottest of chips. And then the whole thing is supposed to have a little air circulating naturally around it. If you put this inside of a tight case, I think it's just going to cook it. Aluminum is a very good conductor. So that's the Pi, such as it is. The way things are going now with cloud computing, you can get yourself a forever free cloud elastic computer from Oracle. And I got one of those, actually got two. And as it turns out, it's a fast machine and it's up all the time. And if what you want is a headless machine that you can use as some kind of a server, well, you kind of don't need a Pi for that. It's when you want to plug your own hard drive in and you want access to the hardware. That's when you want the Pi. I don't know if you guys ever tried this before, but I can kind of show you. If you go to Oracle, right, that's the Oracle Cloud right there. And you can see that it's really empty. I mean, this is idle practically. And it's probably going to have 6.9 reliability. And it's a reasonably fast machine. Certainly it'll give the Pi 4 a run for its money. And I'm not quite sure what the hardware is on this thing. It's probably some Xenon server and you get one core if you're just doing things for free. AWS does the same thing. Here's an AWS cloud. Got it. AWS, I think it's 3. An AWS cloud service, and that's using the Elastic Computer system. Now that has a little bit of load on it. That's where I run my web server. That's Ubuntu. So putting this stuff up on the cloud is generally speaking better if what you want is something that's available to the public. But if what you want is your own server at home, the Pi you could do worse. The Pi is a pretty decent machine. I like the fact that it's got a small form factor and no fan. I hate listening to the fan all day. Right now I'm listening to the fan on my Mini and it seems to be ramping up just because I'm recording. So this is a schematic depiction of the RISC-V block diagram micro engine. And so here you can see he's doing a ROM lookup for the, I'll call it the jump controller that's embedded inside of the CPU. So the CPU becomes a finite state machine that effectively is programmed with ROM lookups. A lot of times what happens is you create a read-only memory that reads out a next address, and then that gets jam loaded into your program counter. And then if you want to jump to that next address, you just basically use the loop inside of the finite state machine to retrieve the program counter's address and use that to look into the memory and get the next operational code. I don't recall if we actually did this in Digital Design 1, but there is a thing called the Richards controller. And the Richards controller essentially takes a decoder and puts it on the output of a counter. And then that decoder gives you the next operational code that you want to execute. So one way in which you can implement this is with a simple decoder on top of some read-only memory. And as the data is read out, it goes into the decoder, and the decoder will tell you what to do for the next register transfer. That's probably about all the microcode I want to cover for now. So let's review what we need to do in order to wrap up the semester. On the 3rd, I think that's Thursday. Today's the 30th. We're going to have homework 11 due, and I'd like to touch on homework 11 before the class ends. On the 17th, that's in December, you're going to have a final, which is due. What I'd like to do is I'd like to stop with the coverage on the microcode, as interesting as that might be, and take a look at your homework 11. We started homework 11. I think we got up to question 17. Does that sound about right? Did people recall?
I remember covering up to question 37.
Oh, 37. Okay, I must have got my wires crossed with the other class. Question 37. Question 37.
Professor,
Yes.
did you decide what day you're going to be releasing the final on Blackboard?
I haven't. Well, let's see. I think you should have 2 weeks to do it. So what that would mean is probably on the 3rd. That would be this Thursday.
Okay, thank you.
Yeah, I think you need it by then, which means I have to finish it. Oh, no, it doesn't. I have to be honest about it. I have to start it. So presumably I'll have a, thank you for asking that question. I've got this on my top priority item now. Do the final. All right, I'll get you a final soon. It'll be a mashup of prior homeworks, and you'll do with 2 attempts, open book, open notes, and it'll be online. You'll be able to go in, print the whole thing, look at it, mark it up, and then enter in the answers at your leisure. So that's the plan. It'll all be administered with Blackboard. I'm just going to take a quick scan. We have about 21 people here on Blackboard right now, including me. So not everybody is here on Blackboard, but I am recording. So if people need to see this later, they should be able to. I know some people didn't quite make it to class and said as much. That's okay. So let's see now. Did we do 37? Or we finished it?
I don't think so.
We didn't do 37? All right. Let's start with 37 then. Hypertransport, formerly known as lightning data transport. You see things like that and you think market speak. Technology for interconnection of computer processors is bidirectional serial, bidirectional serial or parallel, high bandwidth, low latency, point-to-point link that was introduced in 2007. Hypertransport HDX 3.1 runs at 26 gigabits per second. Well, there's just no way you're born knowing that. You'd have to look it up and find out that yes, indeed, this is the case. 26 gigabit. When you see the B is capitalized, that means bytes. That means bytes. So not to put too fine a point on it, that's about 208 gigabits per second. I mean, that is fast. And this is from 2001. So then AMD uses hypertransport to replace the front side bus. That is true. I sort of recall doing that, actually. We did do this. Here comes NUMA. I'm going to make this a little bit larger so we can see it. Whoa, what happened? There it is. So non-uniform memory access. We're used to this terminology now, right? Because we've seen it with the Apple M1 CPU. They have a uniform memory access going through a fabric, but non-uniform memory access, that's characterized by a multi-core system like we are typically using on our Intel processors. So oftentimes what will happen is we'll have RAM on one core that's generally not directly available to RAM on the other core. And so you could have basically a physical socket where your CPU is sitting. RAM can be geographically co-located with respect to that socket. And the other cores may not have direct access to it, so they have to go through another computer to get there. So this is an example where the socket has 8 cores in the chip. And here's another socket with 8 cores in the chip. And you might see this on a reasonably high-end desktop computer or regional data centers computer. And so memory access time depends on the memory location relative to the processor. And yeah, there's 4 separate chips here, and each one has got its own RAM associated with it. And you can kind of see the L3 cache in here is not easily accessible to the L3 cache and the computer that's over in here. So to go in, get that, and bring it over here, that takes an extra step. That's gonna cost you time. And so for that, they use a special bus internal to the motherboard for CPU to CPU communication. What they used to call the front side bus is now the hyper transport thing. So the answer to this question is also true. You know, this NUMA depends on where the memory is. Let's see. Computer cluster is a set of loosely or tightly connected computers that work together so that in many respects they can be viewed as a single system. Unlike grid computers, computer clusters have each node set perform the same task controlled and scheduled by software. What do you think? Is that true or false?
True.
True. That is true. That is true. So the difference between the cluster and you know, this is another application now that I think about it, another application for a Raspberry Pi, because all the nodes can be the same and they can be very close to one another. They can be geographically co-located. So you can build a Pi cluster. And here it is. And you get all your little Raspberry Pis and they'll sell you a little case for them. And then what? Then you can run an experiment. In fact, look, there's a book on Raspberry Pi supercomputers. Have your own cluster. And there's also the Beowulf cluster, which is a very famous cluster that came out of NASA. So sitting around and building clusters might be fun. I don't think you're going to be making any money Bitcoin mining with it, but you might be able to use it to make your next computer animation, your cloud cluster. So that, you know, that sounds like a fun thing to do. Educational, if nothing else. Certainly worth looking at the book and getting it out of the library. So the grid computing, this is very typical to the kind of distributed computing you'll get with BOINC and with the search for extraterrestrials, the SETI project, where the screensavers are doing CPU harvesting. They're harvesting the extra cycles. What do you think about that one? Can you create a super virtual computer using grid computing? Super virtual computer. I wonder what makes it super. Widely distributed computer resources, reach a common goal. When you're doing like the screensavers that are doing the CPU harvesting, this is the kind of grid computing that I'm talking about. And you can see a series of articles that I've written in this topic. This is let's see, what would it be called? There it is, screensavers. So the screensaver computing, the screensaver kicks in and then volunteers the computer into remote job submission systems. And so what you want to do is you want to try and figure out how to get a screensaver to work on every common desktop computer. So I have them for the Macintosh, Windows, and Unix. And so we had separate articles for implementing the screensavers in Windows, Unix, and Mac. And then when the computer goes idle, it volunteers the CPU to try and help solve a job. And so that is a form of distributed computing, parallel computing, truly concurrent computing, because you have multiple machines all vying to execute the same resources. So they can be on the network, they can volunteer their services to a lookup server, and then it can distribute presumably jobs that will keep the CPU busy and not create an undue load on the network. So you need embarrassingly parallel computing problems to solve before anything like that becomes practical. And what that would mean from a practical point of view, you know, what's an embarrassingly parallel program? Well, if you had to do an animation for Disney, every frame is computed separately. So you could dispatch the computation of the geometry for that frame to each CPU. Let's say it takes an hour to compute a frame. Then the CPU becomes CPU bound, and presumably 100 CPUs will run 100 times faster than one CPU. And that's the kind of throughput improvement you would like to get for a truly parallelizable computer program. Parallelizable. So CPU scavenging, that's just the kind of thing we're trying to do when we're volunteering idle computers using a screensaver into the grid. That is I'll call it a strategy, CPU scavenging or cycle scavenging. So that's true. So now we're up to 43. And now we're back to this hypertransport concept. We want to do the non-uniform memory access with multi-processors, and hypertransport is a way to do that. It used to be called the front side bus. So now we've got this idea about cache coherence. It says here, cache coherence is the uniformity of shared resource data that ends up stored in multiple local caches. Cache coherence. Does that sound true to anybody? Is that true or false? What do you think?
True.
That is true. That is true. So what we're trying to do here is get a piece of memory that's local to the CPU and make it so that it has everything in it that's in the non-local memory. That's the cache coherence. If we have direct memory access, it can be filled by a virtual memory address coprocessor while the CPU is busy. So the VMA coprocessor can look ahead, grab the memory out of main memory and put them into the cache so that when the CPU is ready for it, it's right there. And it doesn't have to do a separate request. So now here comes this idea about Zen. they come out with very creative code names. So there's this microarchitecture, and we saw the little lecture now about the microarchitecture. It's from the AMD, and and you may have heard of the Ryzen processor, and perhaps you heard of the rise of Ryzen. It's an article I wrote recently. Ryzen processors have essentially taken, I don't know, market share from Intel because AMD is outsourcing all of its CPU fabrication to Taiwan Semiconductor, and they are able to make 5 nanometer design rule processors. And so they are winning in terms of not just this design, which may or may not be of any use to anyone, but in terms of the number of transistors they can get per unit area. And having done that, they're able to add more cores. And this is part of what's called the core wars, right? We're not having a battle with transistors, we're having a battle with CPU cores. And as a result, AMD seems to be scoring a solid win from Intel on that. And so Zen, yes, it is the code name for the microarchitecture used in Ryzen. So Intel comes along with this idea that instead of competing based on actual transistor size, they're going to build up in 3D. And they do this by creating a new kind of transistor called the FinFET. A field effect transistor is a voltage variable resistor instead of the bipolar junction transistor, or BJT, which is known as a current controlled current source. The metal oxide semiconductor field effect transistor is based on a substrate where the gate is placed on 2, 3, or 4 sides of the channel or wrapped around the channel, forming a double gate structure. So this is what they're fabricating in silicon. So the gate controls the amount of energy that goes from the source to the drain, just like you would pinch on a garden hose and keep the water from flowing. And so that gate essentially can apply a small amount of voltage in order to keep the source from moving electrons to the drain. And so these 3D structures are what they call the fins right in through here. And so this is creating a new kind of transistor. So do you think that's true? Or did I just make that up? Well, the answer on that one is yes, it is true. This is just what they're doing, the FinFET. And so it's a pretty radical way to approach the problem. Instead of making the transistors smaller and smaller, maybe we can build up in 3D, and perhaps we can still get a really reasonable yield during the fabrication process. So now we've got slightly faster switching times, higher current density than mainstream CMOS technology because of the FinFET. And that's true. And what that does is it gives us a bit of a win, right? Because if we can switch faster and have higher current density, then effectively we can pack these things in closer and not worry so much about, let's say, heat waste. But still, you have to be able to have design rules that compete with the marketplace. And we were still waiting for Intel to do that. Here's the simultaneous multi-threading, a technique for improving overall efficiency of superscalar CPUs with hardware multi-threading. Okay, what's a superscalar CPU? You guys should know this by now. Any ideas? You're all very quiet. I'm going to call on people.
This would be true.
That is true. It is true. The superscalar CPUs are running a pipeline where multiple instructions are done in parallel. And with hardware multi-threading, they can jump from one pipeline to the other. So this is true. Next one. I think they're all true. Isn't everything true? So far, everything's been true. Did we have a false yet? I don't think there's been a false. Precision boost overdrive automatically enables. You know, I gotta say, this sounds more like marketing than anything. Automatically enables the CPU to run at speed voltage motherboard supply ranges that allow the CPU to run at an optimal speed power trade-off. It's an AMD proprietary name, so that is marketing, pure and simple. And that is true. So what are we doing? We're throttling down the CPU by reducing the speed and the actual voltages. And this will save us some power and maybe some heat. In fact, when we think about it, the M1 CPU has two high performance cores and two low energy cores. And the low energy cores are designed to make things just run a little bit more efficiently and a little bit cooler. This homework 11 is going on and on and on. But I think we're almost done. We're in the home stretch. Let's see. AMD Zen 2 is to have a 7 nanometer design rule. Well, should be has a 7 nanometer design rule. That means it has twice as many transistors as AMD Zen 1. That's also true. And that has come to pass. And here comes a Ryzen 7 1800X, has 4.8 billion transistors. And this is what happens when you're starting to push down the design rule thing. Yes, you can fit 4.8 billion transistors. And let's keep in mind that when ENIAC came out, there were 18,000 vacuum tubes. So, and the state of the art in the UK at the time for the Colossus computer was 1,800 vacuum tubes. And it was able to decode ciphers from the Nazis during World War II. 1,800 vacuums. And it was kind of a hybrid because it used paper tape and it kept cycling paper tape around, and that was its main memory. The 1800X. 1800X is the Ryzen 7. Integrates 8 cores that makes it a 64-bit octa-core system from 2017. So this is old already. And that's true. This is the core wars. More cores. More cores is better. And maybe the end of that sentence is, we hope. So now here we have a 1800X, a complete system on a chip, integrated DDR4 memory controller, along with entire South Bridge on the die. That means this North Bridge is on that die too. And that has to be true because South Bridge is the slow part. North Bridge is the fast part. These used to be separate chipsets. Now they're all integrated into the same die. The question of whether that makes it a complete system on a chip remains open. Just because it has the DDR memory controller doesn't mean it's a complete system, right? Because what about the memory? Isn't that part of the system? And the answer is yes. Well, is that on the chip? The answer is no. So is it really a complete system? Sort of. They've done more integration. I guess for them, it's a complete system. But it's not like, I don't know, an Arduino where you actually have everything, including the memory, all on the chip. But then again, Arduino is an 8-bit toaster controller and not trying to be a full-blown CPU. It's just a microcontroller. Out-of-order execution, also known as dynamic execution. This was actually introduced in the 60s by IBM. They put it into the IBM 360. It's a paradigm used for most high-performance central processing units to make use of instruction cycles that would otherwise be wasted. So this is speculative execution. In this paradigm, processor executes instructions in an order governed by the availability of the input and execution units rather than by the original order in the program. In doing so, the program can avoid being idle while waiting. In other words, it has nothing else to do. So it just starts executing instructions whether or not it's about to get to those instructions. And in case that it is about to get to the instructions, it says, aha, I already have an answer to that. And here it is. So if it's sitting around waiting for the direct memory access unit to supply it with the next instructions out of main memory, it can sit there and do out of order execution. So that's kind of a way to get a little extra throughput out of these things. How are we doing on time? I think I got another 5 minutes. There are, geez, this goes on and on. There are 64 questions, so we got another 10 questions to go. I don't think we're going to do them in 5 minutes. Just at a guess. Just at a guess. So we just did this one, out of order execution. Let's do this one. Tomaluso's algorithm. Now that comes right out of the book. It's a computer architecture hardware algorithm for dynamic scheduling of instructions that allows the out of order execution and enables more efficient use of multiple execution units. And that is also true. So this is how you do the speculative out of order execution. And that's a thing you can Google. I'll spare you the Googling. So we've talked about pipelining enough. When a machine is pipelined, the overlapped execution of instructions requires the pipeline of functional units and duplication of resources to allow all possible combinations of instructions in the pipeline. What happens if the instruction can't be executed in the pipeline? You get a pipeline miss, right? And so then you have to refill the pipeline, and that's going to cost you your entire implicit parallelism. So that's just about all we have time for. We can maybe squeak in one more question, and I think that'll be it. And if some combination of instructions cannot be accommodated because of a resource conflict, the machine is said to have a structural hazard. And therein lies where you might get a cache miss. This is the kind of thing that will hamper your overall throughput in the CPU. And so that's a true. And so with that, I think we're going to call it quits. I'm going to make a note of the fact that we need to finish our final by next time. And we're stopping at question 57. I'm writing this down. How many more questions do we have? We got like 2 minutes, 57, 58, 59. I'm not going to rush it. We'll pick this up next time. It's raining pretty good out there, so stay safe. And thank you for your time. And I hope you guys have a good day.
Thank you, Professor.
Thank you.
Thank you.
Thank you.
Thank you.